Semigroups and their representations, Lecture 13, Cell partial acts and apex. Let us recall the notion of a transitive act over a semigroup by total transformation. Let S be a semigroup and X be an S act. Recall that X is called transitive, provided that for any xy in X, there is an element A in S such that A applied to X gives Y. Unfortunately, if S has a zero element, then the only transitive S act is the trivial singleton act. If S does not have any zero element, then it can have more transitive acts. For example, the semigroup Tn, so all transformations of the set with n elements, has two transitive acts, the trivial singleton act and the natural act. In general, transitive acts over finite semigroups are controlled in a certain sense by transitive acts over a minimal left ideal. And today we will discuss the theory of acts and of transitive acts by partial transformations, and we will see that this theory is much richer. So let's talk about transitive partial acts. So let S be a semigroup and let X be a partial S act. Just like for usual acts, the act X is called transitive, provided that for any elements X and Y in X, there is an element A in S such that A applied to X is equal to Y. For partial acts, this means, in particular, that every element X in our act is in the domain of some element A of S which acts on X. So, for example, S can act on our X such that all elements of S act as the zero partial transformation, that is, the unique partial transformation with empty domain. And such act cannot be transitive unless X itself is the empty set. And also note that this example is not possible for partial acts over monoids. So if we look at monoid acts, then the identity element of the monoid must act as the identity total transformation. So every element of our act, so in the underlying set, will be in the domain of the identity element. For partial acts, we can define the notion of a quotient of an act. Let X be a partial act over a semigroup S. It doesn't have to be transitive. Let Y be an S-invariant subset of X. Then we can consider the set Z, which is X minus Y. For an element A in S, we define a partial action of A on Z by restricting this action from X in the following sense. Consider the element A when it acts on X. So we denote it by A dot sub X. And let us define the action of A on Z, and we denote it by A dot sub Z. So we postulate, if we take an element U in Z, this element belongs to the domain of A acting on Z, if and only if U belongs to the domain of A acting on X, and additionally, A applied to U in X gives an element in Z. And if the latter condition is satisfied, we define that A acts in Z on U and gives the same outcome as if A acts in X on U. Proposition, the above, defines on Z the structure of a partial S act, called the quotient of X modulo Y and denoted by X divided by Y. From now on, we will also drop the subscript Z in the notation for the action. Proof. Let A and B be two elements in S. So we need to prove that the domains of the elements AB applied to something and A applied to B applied to something coincide on Z, and that the two partial transformations coincide on this common domain. So there are two things to prove. So the domain of The domain of A applied to B applied to something consists of all elements U in Z, such that B applied to U belongs to Z. Moreover, it belongs to the domain of A applied to something, and A applied to B applied to U belongs to Z. And since X was a partial act over S, each such U also belongs to the domain of AB applied to something in X, and also for such U, AB applied to U is equal to A applied to B applied to U. Conversely, if AB applied to U belongs to Z, then U must be in the domain of B applied to something, and moreover, B applied to U must be in Z, because if it's outside Z, it is in Y, but then applying A to it, we cannot go outside Y because Y is S invariant. So this completes the proof of the proposition. Now we can use this construction to describe quotient acts for actions on ideals. So let S be a semigroup and I a left ideal of S. Then I is an S-act by restricting the left regular S-act S to the invariant subset I. And this is due to the fact that the notion of a left ideal is exactly the same thing as an invariant subset for the left regular act. If we have two left ideals in S, I and J, and I is a subset of J, then I is an invariant subset of the S-act J. So we can consider the quotient of J modulo I. Let's note that this quotient is usually only a partial S-act, despite of the fact that both I and J, which we started from, were acts by total transformations. Here is an example. Consider the monogenic semigroup S, which is generated by one element A, which satisfies the relation that A to the power 4 is equal to A to the power 5. Then S consists of four elements, A squared, A cubed, and A to the power 4, and it has the following Cayley table. A to the power I multiplied with A to the power j gives us A to the power I plus j, where A to the power 4 is equal to A to the power 5, and so on. So in the left regular act S, the element A acts as the following transformation. So multiplication with A moves A to A squared to A cubed to A to the power 4, and A to the power 4 to A to the power 4. We have the left ideal J of S, which consists of elements A squared, A cubed, and A to the power 4. And in this S act, so in this ideal, multiplication with A gives us the following transformation. So A squared is mapped to A to the power 3, A to the power 3 is mapped to A to the power 4, and A to the power 4 is mapped to A to the power 4. Next we have the left ideal I of S, which consists of the element A to the power 4. In the corresponding S act, the element A acts as the identity transformation. It maps A to the power 4 to A to the power 4. So I is an S-invariant subset of J, and we can consider the quotient of J modulo I, which as a set is equal to A to the power 2 and A to the power 3, so it has two elements. Note that A maps A squared to A to the power 3, it still belongs to our set. However, A to the power 3 is mapped to A to the power 4, which is outside of our set. So this means that the element A acts on the quotient act J modulo I as the partial transformation with domain consisting of one element, A to the power 2, and this element is sent to A to the power 3. So this is the action of A on the quotient set. The quotient set has two elements, but the domain of A has only one element. So this completes this example. Now we can discuss the notion of a cell partial act. Let A be an element of a semigroup S. Consider the principal left ideal generated by A. So this is an ideal J, and it is equal to S upper 1 times A. Then the left class LA of the element A is a subset of J. And the complement I of the left class LA inside J is a left ideal. And let's note that I, by definition, really depends on the left class LA and not on the element A itself. Definition: the partial S-act J modulo I is called the cell partial act and is denoted by CA or C sub LA. And note that the underlying set of this cell partial act is exactly the left cell of the element A. Also note that CLA is an act by total transformations if LA is a minimal left ideal, so if I is the empty set. Here is an alternative description, more precise. We can alternatively describe cell partial acts as follows. So let L be a left cell of a semigroup S. Define on L the structure of a partial S act as follows. For an element A in S and an element V in L, the element V belongs to the domain of A acting on our left cell, if and only if the product AV belongs to the left cell. And in the latter case, so if AV belongs to L, A acts on V and gives AV. So for example, if G is a group, it has a unique left cell, namely the group itself, and in this case the cell partial act, which corresponds to this unique left cell, is in fact the left regular act. So this left cell is the minimal ideal. So in particular, in this case, it's an act by total transformations and not a partial act. Here is a less trivial example. Consider the semigroup IS2 of all partial injections on the set 1, 2. Recall that the left classes of IS2 are indexed by domains of the elements, that is, by subsets of 1, 2. Consider the left class L that consists of all elements whose domain is 1. Then this left class has two elements, alpha 1 and alpha 2. So here alpha 1 sends 1 to 1 and alpha 2 sends 1 to 2. So as a set, our cell partial act CL is just L. So it has two elements, alpha 1 and alpha 2. So how does the semigroup IS2 act on this set? The semigroup IS2 has 7 elements, 2 elements of rank 2, 4 elements of rank 1, and 1 element of rank 0. So the unique element of rank 0, that's the 0 element of IS2, it's the element which has empty domain on 1, 2. And this element satisfies that if we multiply 0 with alpha 1, we get 0, and if we multiply 0 with alpha 2, we get 0. And 0 as an element of IS2 doesn't belong to L. This means that our element 0 of IS2 has empty domain as a transformation of our cell partial act CL. Next, we have two elements of rank 2. These are the invertible elements. These are the elements of the symmetric group S2. So we have the identity element E and the elementary transposition 1, 2, which swaps 1 and 2. Of course, E acts on our cell partial act as the identity, and the transposition of 1 and 2, it swaps alpha 1 and alpha 2, because this transposition after alpha 1 gives alpha 2, and this transposition after alpha 2 gives alpha 1. Next, let us talk about elements of rank 1. The element alpha 1 satisfies that alpha 1 after alpha 1 equals alpha 1, and alpha 1 after alpha 2 equals 0, the nowhere defined element. Therefore, alpha 1 has domain alpha 1 on CL and acts as the identity transformation of this domain. The element alpha 2 multiplies in the following way. Alpha 2 after alpha 1 is alpha 2, and alpha 2 after alpha 2 is 0. Therefore, alpha 2 has domain alpha 1 on our act CL, and it maps alpha 1 to alpha 2. Similarly, we have the element B1 of rank 1, whose domain is 2, and which maps 2 to 1. So this element has domain alpha 2 on CL, and it maps alpha 2 to alpha 1, because beta 1 after alpha 2 is alpha 1, and beta 1 after alpha 1 is 0. And finally, the element beta 2, which has domain 2 and maps 2 to 2, has domain alpha 2 on CL, and it maps alpha 2 to alpha 2. So this completes this example. Now we can talk about the annihilator of an act. Let X be a partial act over a semigroup S. Definition: we will say that an element A in S annihilates X if it acts on X as the partial transformation with empty domain. Terminology: the set of all elements in S which annihilate X is called the annihilator of X and denoted by annihilator in S of X. And directly from the definition it is clear that the annihilator of any act or of any partial act is a two-sided ideal of X. For example, if S acts on X by total transformation, then the annihilator of X in S is empty. Example 2. In our previous less trivial example of the partial IS2 act CL, where L was the left cell consisting of alpha 1 and alpha 2, the annihilator of this act consists just of the rank 0 element 0. The element 0 annihilates it, and all other elements of IS2 do not annihilate it. Now we can define the notion of an apex. Theorem: let X be a partial transitive act over a finite semigroup S. Then the set S minus the annihilator of X in S contains a unique two-sided class J that is minimal in this set with respect to the two-sided order. And terminology: this unique two-sided class J is called the apex of X and denoted apex of X. For example, if S contains a 0 element 0 and X is an act by total transformations, then X is the trivial singleton act. Transitive acts by total transformations over a semigroup with 0 are trivial. So X is a trivial singleton act and its apex is exactly 0. So it's a two-sided cell which consists of 0. Example 2, again in our less trivial example of the partial IS2 act CL, where L is equal to alpha 1 and alpha 2, the apex of CL is the two-sided class of all elements of rank 1. So the elements of rank 0 annihilate it, the elements of rank 1 and 2 do not annihilate it. And this set has a unique minimal J class, which is the class of elements of rank 1. So this J consists of alpha 1, alpha 2, beta 1, and beta 2. That's the apex of this CL. Now let's prove the theorem. Assume that J is a two-sided class that is minimal in S minus the annihilator of X with respect to the two-sided order. We claim that each element U in our act X is in the domain of some element A in this J class J. If not, then the subset Y of X, which consists of all elements in X which are not in the domain of any element in our two-sided class J, then this subset is not empty. Also, for an element V in Y, A in J, and B in S, we have that A applied to B applied to V is equal to AB applied to V. In particular, both sides of this equality are defined at the same time. Now, AB either belongs to J or it belongs to some J class which is strictly smaller than J, and then it annihilates X by the minimality of J. So this means that AB applied to V, the right-hand side, is not defined. But then this means that B applied to V, if it is defined, it cannot be in the domain of A. In other words, this shows that Y is an S-invariant subset of X. and then y should be equal to x due to transitivity, and this contradicts our choice of j. J cannot be in the annihilator of x by definition. So this means that j applied to any element u is a non-empty subset of x. Also, if we apply s to j applied to u, so that's a subset of sj applied to u, and that's a subset of j applied to u. Which means that j applied to any element of x is S-invariant and not empty, so it must coincide with x by transitivity. Therefore, j applied to u is equal to x, so x is a transitive j act. Now, let us assume that j1 and j2 are two j classes that are minimal in our set S minus the annihilator with respect to the two-sided order. Note that at least one such minimal j class exists because we assume S to be finite. Then, for any element A in j1 and B in j2, the product AB must annihilate x. So it should be less than or equal to j1, and it should be less than or equal to j2. But j1 and j2, they are not comparable due to our assumption of minimality in the two-sided order. So AB must be strictly smaller than both j1 and j2, and therefore it must annihilate x. At the same time, on the previous slide, we proved that j1 applied to x is x, and j2 applied to x is x. And so j1, j2 applied to x, that's equal to j1 applied to j2 applied to x, that's j1 applied to x, that's x. And this gives us a contradiction which proves that we cannot have two different minimal ideals in our set. And this completes the proof of the theorem. Now we prove an important property of an apex is that the apex is always a regular two-sided class. So corollary, let x be a partial transitive act over a finite semigroup S. Then the apex of x is a regular J class. Proof. Let J be the apex of x. In the proof of our previous theorem, we saw that J applied to x is equal to x. Take an element u in x, then there is an element A in our J class J, such that u is in the domain of A. And there is an element B in J, such that A applied to u is in the domain of B. But then u is in the domain of BA, and so BA must be an element in J. So we have two elements in J such that their product is in J. But this means that J is a regular class by one of our characterization of regular two-sided classes in lecture 6. Next, let, as an example, describe the apex of a regular cell partial act. So let L be a left cell of a semigroup S. Assume that L is regular, that is, it contains some idempotent E. Proposition: in this case, the apex of the cell partial act CL is the J class containing E. Proof: since E times E is E, the element E, and hence any element from JE, doesn't annihilate our cell act. On the other hand, if we have an element A in our semigroup which is not greater than or equal to J sub E in the two-sided order, then A applied to U cannot belong to JE for any U in L. Therefore, U doesn't belong to the domain of A acting on our cell partial act CL, and this means that such A must annihilate CL. So indeed, J sub E is the minimal with respect to the two-sided order, two-sided class, which does not annihilate our act. Next, let us discuss transitivity of cell acts. Proposition: let L be a left cell of a semigroup S. Then the cell partial act CL is either transitive or L is a singleton and the annihilator of CL in S is equal to the whole of S. Proof: Let U and V be two elements in L. Then we know that there exist elements A and B in S upper 1, such that A applied to U, so AU is equal to V, and BV is equal to U. So if L is not a singleton, then we directly see that CL is transitive. If L is a singleton, then CL is not transitive if and only if the annihilator of CL is the whole semigroup. Corollary: any cell partial act over a monoid is transitive, and that's because over a monoid we cannot have that the annihilator is the whole monoid. Here is an example. Consider the monogenic semigroup S, which is generated by element A such that a to the power 3 is equal to a to the power 4. Then S consists of three elements, a squared, and a to the power 3, which is a zero element of the semigroup, with the obvious multiplication. All green cells of S are singletons. In particular, we have three left cells: L1, which has only A, L2, which has A squared, and L3, which has A to the power 3. Note that L3 is a regular two-sided cell and the left cell because A to the power 3 is an idempotent, but the two other left cells are not regular. The cell act which corresponds to L3 is just the trivial singleton S act. The cell partial acts CL1 and CL2 are partial singleton acts for which the annihilator is the whole of S. So in particular, these two partial singleton acts are isomorphic. And in general, we have the following theorem which describes isomorphisms of some cell partial acts. Proposition: let L1 and L2 be two left cells of a semigroup S. Assume that L1 and L2 belong to the same two-sided cell. Then the corresponding partial acts CL1 and CL2 are isomorphic. Proof: of course, we assume that L1 is different from L2, otherwise we have nothing to prove. Let U be an element in L1 and V be an element in L2 intersection with RU, with the right class of U. Then there are elements x and y in S such that U is equal to Vx and V is equal to Uy. And then we have seen, when we discussed green relations, that in this case the maps which send R to Rx and T to Ty are mutually inverse bijections between L2 and Ly. And these maps are given by right multiplication, and this of course commutes with left multiplication, and so these maps commute with the left multiplication which defines the partial act structure. So these maps are also homomorphisms of partial acts. So we have bijective homomorphisms of partial acts, so these are mutually inverse isomorphisms. Some problems and questions at the end. Problem question 1. Explain with all details why C upper 1a minus LA is a left ideal. Problem question 2. Check with all details that the annihilator of an act is a two-sided ideal. Problem question 3. Construct a transitive partial act over IS2 that is not isomorphic to any cell partial act. Problem question 4. Describe explicitly all cell partial acts over PT2. And problem question 5. Spell out all the details in the proof of the last proposition. Thank you very much and see you next time.